Hi everyone and welcome back. So we have been discussing about centering right now, and by now you would have already known that the centering process or the densification which occurs during centering is synonymous with shrinkage. Okay, and when you talk about shrinkage, you will have to look at the dimensional tolerances of the component, right? Because shrinkage will lead to some reduction in the dimensions, right? So in this class we are going to look at that particular aspect as to what are the parameters which control the dimensional tolerances, and how do you maintain these tolerances in the centering process. So as I said, this dimensional control is related to shrinkage. And the shrinkage is related to the green density of the compact. It is in fact inversely proportional to the green density. Right, and this in turn, the green density in turn depends on the compaction pressure and the method of compaction. So while talking about the dimensional control, we will have to consider both of these. So let's talk about the compaction pressure first and see what is its effect on the dimensional control. So compaction pressure is related to the dimensional control indirectly through the green density. That is what we see here also. The green density is related to shrinkage, which in turn is related to the dimensional control. Okay. So let's see what way this compaction pressure will affect the green density. First of all, pressing the powder before sintering leads to two things which are beneficial for the sintering process. One is reduction in the porosity, and secondly, increase in the dislocation density. As we have seen before, lower the porosity, lower will be the shrinkage. And therefore it becomes easier to maintain the dimensions of the sintered part. Okay. And the second one, that is the dislocation density, comes into picture because we have seen that the compaction process also leads to plastic deformation as the powder is being pressed, and as the pressure is increased beyond the yield point of the material, the dislocations are generated and the dislocation density increases, and this kind of leads to enhanced diffusion because one of the mechanisms of diffusion, that is plastic flow, is controlled by the dislocations. So when you have higher dislocation density, in case of metals, you can also expect an enhanced diffusion, and that will give rise to a better densification also. Okay, so this is how, when you press the compact, it helps the sintering process in terms of these two factors. Okay, so now if you see the effect of the compaction pressure on the densification and the shrinkage that occurs during sintering, that can be demonstrated with the help of plots like this. The densification during sintering is represented by the neck size ratio x by d. So let's see how that varies with the compaction pressure. So as the compaction pressure is increased, the densification will also increase in this manner. Okay, that's one thing, and this can also be demonstrated with a similar curve. When you see the densification as a function of the sintering time at different compaction pressures. Okay, so let us now plot the densification with the sintering time and see with different compaction pressure how this densification varies. The first curve is with no pressure. So let's say we are talking about sintering a copper powder at 1020 degrees Celsius. Okay, and as you increase the pressure, you can see the densification also increases. Right? So for a given sintering time, you can see higher pressure will give rise to higher densification. And now if you look at the shrinkage, delta L by L naught, now the trend will be completely opposite to the density. That means for zero pressure, you have high shrinkage, and as you increase the pressure, it decreases, and therefore it is easier to maintain the dimensional control when the compaction is done at high pressure. So this comes from the fact that shrinkage is inversely proportional to the grain density, as I said before. So when the compaction pressure is increased, the grain density also increases, and therefore the shrinkage will decrease, as you could see from here, right? And therefore it is easier to maintain the dimensional control when the powder is pressed at higher pressure. Now, as I said, we have to also look at the compaction method, because every method will give rise to a different kind of packing of powders and may lead to a different grain density. So let us compare two methods. One is the simplest one, that is uniaxial pressing, and we will take another one to compare it with the uniaxial pressing. So in case of uniaxial pressing or die compaction, we have seen that there are chances of occurrence of pressure gradient in the compact during the pressing operation, and this will lead to gradients in the density as well. Okay, so like this, you may have gradients in the density in the die compaction process. These density gradients will lead to a gradient in the shrinkage also, and therefore the dimensional changes across the compact will not be uniform, and as a result of that anisotropic shrinkage, the dimensional control will be really difficult to maintain. Okay. right? So this density gradient will lead to anisotropic shrinkage, which will adversely affect the dimensional tolerances. Okay. In the die compaction process, minimum dimensional change can be achieved by large powders, high compaction pressure, low sintering temperature, short sintering time, small compact height, and uniform geometries. So all this can minimize the dimensional change or distortion in case of the die compaction process. But the problem is some of these attributes are also detrimental to the compact strength, and some of them can also create problems such as die wear and things like that. Hence, it is difficult to maintain the dimensional tolerances by the die compaction process, as I said before. Now, in comparison to die compaction, if you consider one more method, which is kind of more uniform in terms of generating the density, then we can also see, the shrinkage will be also uniform, and therefore the dimensional tolerances will be much better in that case. So let us consider the PIM process, wherein the forming which takes place is hydrostatic in nature. Right, so here the pressing is uniform, and as a result of that, in the green compact, if you look at a similar compact that we had seen for the die compaction, you can obtain a uniform density across the compact, and therefore this will lead to isotropic shrinkage, unlike the die compaction method, which leads to anisotropic shrinkage. And therefore you can see that the dimension is maintained and you can have excellent dimensional tolerances. Right? So this is how the compaction method will also influence the shrinkage and the dimensional tolerance in the sintering process. As much as 16% shrinkage can occur during sintering of a compact made by the powder injection molding process. But in spite of that, it provides minimum distortion of the sintered compact. This is due to the fact that the density is uniform and therefore the shrinkage is also uniform, and so the dimensional changes are also uniform across the compact, and therefore the distortion is minimum, right? So this is how you can see how the compaction method will also influence the dimensional control during the sintering process. Okay, so before we finish, let us take a moment to summarize this lecture. So to summarize, we can say that the compaction pressure and the compaction method both have an influence on the dimensional control during the sintering process. And this dimensional control is basically related to the shrinkage, which is in turn related to the grid density of the compact. Higher the grid density, lower will be the shrinkage, and therefore better will be the dimensional control, right? We know that higher compaction pressure leads to higher density and therefore lower shrinkage, right? So in order to maintain dimensional control, a high pressure compaction is recommended. Okay. On the other hand, when you compare the compaction methods used for pressing the powder one method may be better than the other in terms of giving a better dimensional control. For example, if you compare the die compaction process with the powder injection molding, then here you have density gradients which will give rise to non-uniform or anisotropic shrinkage. Which will lead to some distortion in the sintered part, and therefore dimensional control becomes difficult for compacts made by the die compaction method. PIM on the other hand is hydrostatic in nature and gives rise to uniform density. And this will lead to isotropic shrinkage and hence a better dimension control with minimum distortion of the part can be achieved. Right, so the objective will be always to have a uniform part and no distortion, and therefore depending on the part shape size and the complexity, an appropriate compaction method should be chosen so that at the end of the sintering process a part with the desired shape and size can be obtained. And with that we come to the end of this particular lecture. Thank you for your attention.